Hydrogen is a chemical element in the periodic table that has the symbol H and the atomic number 1. At standard temperature and pressure, it is a colorless, odorless, nonmetallic, univalent, tasteless, highly flammable diatomic gas, dihydrogen. With an atomic mass of 1.00794 grams per mole, hydrogen is the lightest element. It is also the most abundant, constituting roughly 75% of the universe's elemental matter. Stars in their main sequence are overwhelmingly composed of hydrogen in its plasma state. Elemental hydrogen is relatively rare on Earth and is industrially produced from hydrocarbons, after which most free hydrogen is used captively, meaning locally at the production site, with the largest markets about equally divided between fossil fuel upgrading, for example hydrocracking, and in ammonia production, mostly for the fertilizer market. The most common naturally occurring isotope of hydrogen contains 1 electron and an atomic nucleus of 1 proton. In ionic compounds, it can take on either a positive charge, becoming a cation, a bare proton, or a negative charge, becoming an anion known as a hydride. Hydrogen can form compounds with most elements and is present in water and all organic compounds. It plays a particularly important role in acid-base chemistry, in which many reactions involve the exchange of protons between soluble molecules. As the only element for which the Schrödinger equation can be solved analytically, study of energetics and bonding of the hydrogen atom has played a key role in the development of quantum mechanics. Section 1. Nomenclature. The word hydrogen has several different meanings. 1. The name of an element. 2. An atom, sometimes called H dot, that is abundant in space but essentially absent on Earth because it dimerizes. 3. A diatomic molecule that occurs naturally in trace amounts in Earth's atmosphere. Chemists increasingly refer to H subscript 2 as dihydrogen, to distinguish this molecule from atomic hydrogen and hydrogen found in other compounds. 4. The atomic constituent within all organic compounds, water, and many other chemical compounds. The elemental forms of hydrogen should not be confused with hydrogen as it appears in chemical compounds. Section 2. History. Subsection 1. Discovery of dihydrogen. Hydrogen gas, dihydrogen, was first artificially produced and formally described by T. von Hohenheim, also known as Paracelsus, 1493 to 1541, via the mixing of metals with strong acids. He was unaware that the flammable gas produced by this chemical reaction was a new chemical element. In 1671, Robert Boyle rediscovered and described the reaction between iron filings and dilute acids, which results in the production of hydrogen gas. In 1766, Henry Cavendish was the first to recognize hydrogen gas as a discrete substance by identifying the gas from a metal-acid reaction as inflammable air, and further finding that the gas produces water when burned. Cavendish had stumbled on hydrogen when experimenting with acids and mercury. Although he wrongly assumed that hydrogen was a liberated component of mercury, rather than the acid, he was still able to accurately describe several key properties of hydrogen. He is usually given credit with its discovery as an element. In 1783, Antoine Lavoisier gave the element the name of hydrogen, when he, with Laplace, reproduced Cavendish's finding that water is produced when hydrogen is burned. Lavoisier's name for the gas went out. One of the first uses of dihydrogen was for balloons. The dihydrogen was obtained by reacting sulfuric acid and metallic iron. Infamously, dihydrogen was used in the Hindenburg airship that was destroyed in a mid-air fire. Subsection 2. Role and history of quantum theory. Because of its relatively simple atomic structure, consisting only of a proton and an electron, the hydrogen atom, together with the spectrum of light produced from it or absorbed by it, has been central to the development of the theory of atomic structure. Furthermore, the corresponding simplicity of the hydrogen molecule and the corresponding cation, dihydrogen, allowed further understanding of the nature of the chemical bond, which followed shortly after the quantum mechanical treatment of the hydrogen atom had been developed in the mid-1920s. One of the first quantum effects to be explicitly noted, but not understood at the time, was Maxwell's observation, half a century before full quantum mechanical theory arrived. He observed that the specific heat capacity of dihydrogen unaccountably departs from that of a diatomic gas below room temperature and begins to increasingly resemble that of a monatomic gas at cryogenic temperatures. According to quantum theory, this behavior arises from the spacing of the quantized rotational energy levels, which are particularly wide-spaced in dihydrogen because of its low mass. These widely spaced levels inhibit equal partition of heat energy into rotational motion in hydrogen at low temperatures. Diatomic gases composed of heavier atoms do not have such widely spaced levels and do not exhibit the same effect. Section 3. Natural occurrence. Hydrogen is the most abundant element in the universe, making up 75% of normal matter by mass and over 90% by number of atoms. This element is found in great abundance in stars and gas giant planets. Molecular clouds of dihydrogen are associated with star formation. Hydrogen plays a vital role in powering stars through proton-proton reaction, nuclear fusion. Throughout the universe, hydrogen is mostly found in the atomic and plasma states, whose properties are quite different from molecular hydrogen. As a plasma, hydrogen's electron and proton are not bound together, resulting in very high electrical conductivity and high emissivity, producing the light from the sun and other stars. The charged particles are highly influenced by magnetic and electric fields. For example, in the solar wind, they interact with Earth's magnetosphere, giving rise to Birkeland currents and the aurora. Hydrogen is found in the neutral atomic state in the interstellar medium. The large amount of neutral hydrogen found in the damped Lyman alpha systems is thought to dominate the cosmological baryonic destiny of the universe up to redshift z=4. Under ordinary conditions on Earth, elemental hydrogen exists as the diatomic gas H2 for data see table. However, hydrogen gas is very rare in the Earth's atmosphere, 1 part per million by volume, because of its light weight, which enables it to escape from Earth's gravity more easily than heavier gases. Although H atoms and H2 molecules are abundant in interstellar space, they are difficult to generate, concentrate, and purify on Earth. Most of Earth's hydrogen is in the form of chemical compounds, such as hydrocarbons and water, mostly water. Hydrogen gas is produced by some bacteria and algae, and is a natural component of flatus. Methane is a hydrogen source of increasing importance. Section 4. The hydrogen atom. Subsection 1. Electron energy levels. The ground state energy level of the electron in a hydrogen atom is 13.6 electron volts, which is equivalent to an ultraviolet photon of roughly 92 nanometers. The energy levels of hydrogen can be calculated fairly accurately using the Bohr model of the atom, which conceptualizes the electron as orbiting the proton, an analogy to the Earth's orbit of the Sun. However, electrons and protons are attracted to one another by the electromagnetic force, while planets and celestial objects are attracted to each other by gravity. Because of the discretization of angular momentum postulated in early quantum mechanics by Bohr, the electron in the Bohr model can only occupy certain allowed distances from the proton, and therefore only certain allowed energies. A more accurate description of the hydrogen atom comes from a purely quantum mechanical treatment that uses a Schrödinger equation to calculate the probability density of the electron around the proton. Treating the electron as a matter wave reproduces chemical results such as shape of the hydrogen atom more naturally than the particle-based Bohr model, although the energy and spectral results are the same. Modeling the system fully using reduced mass of nucleus and electrons, as one would do in a two-body problem in celestial mechanics, yields an even better formula for the hydrogen spectra, and also the correct spectral shifts for isotopes deuterium and tritium. Very small adjustments in energy levels in the hydrogen atom, which correspond to actual spectral effects, may be determined by using a full quantum mechanical theory which corrects for the effects of special relativity and by accounting for quantum effects arising from the production of virtual particles in the vacuum as a result of electric fields. See quantum electrodynamics. In hydrogen gas, the electronic ground state energy level is split into hyperfine structure levels because of magnetic effects of the quantum mechanical spin of the electron and proton. The energy of the atom when the proton and electron spins are aligned is higher than when they are not aligned. The transition between these two states can occur through emission of a photon through a magnetic dipole transition. Radio telescopes can detect the radiation produced in this process, which is used to map the distribution of hydrogen in the galaxy. Subsection 2. Isotopes. Hydrogen has 3 naturally occurring isotopes, denoted H1, H2, and H3. Other highly unstable nuclei, like H4 to H7, have been synthesized in the laboratory but not observed in nature. H1 is the most common hydrogen isotope, with an abundance of more than 99.98%. Because the nucleus of this isotope consists of only a single proton, it is given the descriptive but rarely used formal name protium. H2, the other stable hydrogen isotope, is known as deuterium and contains 1 proton and 1 neutron in its nucleus. Deuterium comprises 0.0026 to 0.0184% of all hydrogen on Earth. It is not radioactive and does not represent a significant toxicity hazard. Water-enriched molecules that include deuterium instead of normal hydrogen is called heavy water. Deuterium and its compounds are used as a non-radioactive label in chemical experience in solvents for H1 NMR spectroscopy. Heavy water is used as a neutron moderator and coolant for nuclear reactors. Deuterium is also a potential fuel for commercial nuclear fusion. H3 is known as tritium and contains 1 proton and 2 neutrons in its nucleus. It is radioactive, decays through beta decay with a half-life of 12.32 years. Small amounts of tritium occur naturally because of the interaction of cosmic rays with atmospheric gases. Tritium has also been released during nuclear weapon tests. It is used in nuclear fusion reactions, such as a tracer in isotope geochemistry, and specialized in self-powering lighting devices. Tritium is also used in chemical and biological labeling experiments as radioactive label. Hydrogen is the only element that has different names for all of its isotopes in common use today. During the early study of radioactivity, various heavy radioactive isotopes were given names, but such names are no longer used. The symbols D and T, instead of H2 and H3, are sometimes used for deuterium and tritium, but the corresponding symbol P is already in use for phosphorus and thus not available for protium. epoch states that while this use is common, it is not preferred. Section 5. Elemental molecular forms. There are 2 types of diatomic hydrogen molecules that differ by the relative spin of their nuclei. In the orthohydrogen form, the spins of the 2 protons are parallel and form a triplet state. In the parahydrogen form, the spins are antiparallel and form a singlet. At standard temperature and pressure, hydrogen gas contains about 25% of the para form and 75% of the ortho form, also known as the normal form. The equilibrium ratio of orthohydrogen to parahydrogen depends on temperature, but since the ortho form is an excited state and has a higher energy than the para form, it is unstable and cannot be purified. At very low temperatures, the equilibrium state is composed almost exclusively of the para form. The physical properties of pure parahydrogen differ slightly from those of the normal form. The ortho/para distinction also occurs in other hydrogen-containing molecules or functional groups, such as water and methylene. The uncatalyzed interconversion between para and ortho dihydrogen increases with increasing temperature. Thus, rapidly condensed dihydrogen contains large quantities of the high-energy ortho form that convert to the para form very slowly. The ortho over para ratio in condensed dihydrogen is an important consideration in the preparation and storage of liquid hydrogen. The conversion from ortho to para is exothermic and produces enough heat to evaporate the hydrogen liquid leading to the loss of the liquefied material. Catalysts for the ortho-para interconversion, such as iron compounds, are used during hydrogen cooling. Section 6. Chemical and physical properties. The solubility and adsorption characteristics of hydrogen with various metals are very important in metallurgy, as many metals can suffer hydrogen embrittlement, and in developing safe ways to store it for use as a fuel. Hydrogen is highly soluble in many compounds and composed of rare earth metals and transition metals, and can be dissolved in both crystalline and amorphous metals. Hydrogen's solubility in metals is influenced by local distortions or impurities in the metal crystal lattice. Subsection 1. Combustion. Hydrogen gas is highly flammable and will burn at concentrations as low as 4% dihydrogen in air. The enthalpy of combustion for hydrogen is negative 286 kilojoules per mole. It combusts according to the following balanced equation: 2-dihydrogen G plus dioxygen G converts to 2H2O1 plus 572 kilojoules. When mixed with oxygen across a wide range of proportions, hydrogen explodes upon ignition. Hydrogen and oxygen flames are nearly invisible to the naked eye, as illustrated by the faintness of flame from the main space shuttle engines, as opposed to the easily visible flames from the shuttle boosters. Thus it is difficult to visually detect if a hydrogen leak is burning. Although it is widely believed that the Hindenburg Zeppelin burned because a spark ignited the hydrogen gas it contained, the flames seen at right are actually from the covering skin of the Zeppelin, which contained carbon and pyrophoric aluminum powder that may have started the fire. Another characteristic of hydrogen flame is that the flames tend to ascend rapidly with the gas in the air, causing less damage than hydrocarbon fires. 2/3 of the Hindenburg passengers survived, partly for this reason. H2 reacts directly with other oxidizing elements. A violent and spontaneous reaction can occur at room temperature with chlorine and fluorine, forming the corresponding hydrogen halides HCl and HF. Section 7. Compounds. Subsection 1. Covalent and organic compounds. While dihydrogen is not very reactive under standard conditions, it does form compounds with most elements. Millions of hydrocarbons are known, but they are not formed by the direct reaction of elementary hydrogen and carbon. Hydrogen can also form compounds with elements that are more electronegative, such as halogens, like fluorine, chlorine, bromine, and iodine, and chalcogens, like oxygen, sulfur, and selenium. In these compounds, hydrogen takes on a partial positive charge. When bonded to fluorine, oxygen, or nitrogen, hydrogen can participate in a form of strong non-covalent bonding called hydrogen bonding, which is critical to the stability of many biological molecules. Hydrogen also forms compounds with less electronegative elements, such as metals and metalloids, in which it takes on a partial negative charge. These compounds are often known as hydrides. Hydrogen forms a vast array of compounds with carbon. Because of their general association with living things, these compounds came to be called organic compounds. The study of their properties is known as organic chemistry, and the study in the context of living organisms is known as biochemistry. By some definitions, organic compounds are only required to contain carbon, as a classical historical example, urea. However, most of them also contain hydrogen, and since it is the carbon-hydrogen bond which gives this class of compounds most of its particular chemical characteristics, carbon-hydrogen bonds are required in some definitions of the word organic in chemistry. This latter definition is not perfect, however, as in this definition urea would not be included as an organic compound. In inorganic chemistry, hydrides can also serve as bridging ligands that link two metal centers in a coordination complex. This function is particularly common in group 13 elements, especially in boranes, boron hydrides, and aluminum complexes, as well as in clustered carboranes. Subsection 2. Hydrides. Compounds of hydrogen are often called hydrides, a term that is used fairly loosely. To chemists, the term hydride usually implies that the H atom has acquired a negative or anionic character, denoted H-. The hydride anion is a convenient bookkeeping tool that does not exist per se. Alkali metal hydrides, for example sodium hydride, NaH, are polymeric and have no solution chemistry. Electrolysis of molten lithium hydride, LiH, produces a stoichiometric quantity of hydrogen at the anode. In lithium aluminum hydride, the aluminum hydride anion carries hydridic centers firmly attached to the aluminum 3. Although hydrides can be formed with almost all main group elements, the number and combination of possible compounds varies widely. For example, there are over 100 binary boron hydrides known, but only one binary aluminum hydride. Binary indium hydride has not yet been identified, although larger complexes exist. Subsection 3. Protons and acids. Oxidation of dihydrogen formally gives a proton, H+. This species is central to the discussion of acids, although the term proton is used loosely to refer to the positively charged or cationic hydrogen, denoted H+. A bare proton, H+, cannot exist in solution because of its strong tendency to attach itself to atoms or molecules with electrons. To avoid the convenient fiction of naked solvated proton in solution, acidic aqueous solutions are sometimes considered to contain the hydronium ion, trihydrogen oxide, organized into clusters to form nonohydrogen tetroxide plus. Other oxonium ions are found when water is in solution with other solvents. Although exotic on Earth, one of the most common ions in the universe is a trihydrogen plus ion, known as protonated molecular hydrogen, or the triatomic hydrogen cation. Section 8. Production. Dihydrogen is produced in chemistry and biology laboratories, often as a byproduct of other reactions, in industry for the hydrogenation of unsaturated substrates, and in nature as a means of expelling reducing equivalents in biochemical reactions. Subsection 1. Laboratory syntheses. In the laboratory, dihydrogen is usually prepared by the reaction of acids on metals such as zinc. Zinc plus 2H+ converts to zinc with the +2 charge plus dihydrogen. Aluminum produces dihydrogen upon treatment with acids, but also with base. 2 aluminum plus 6 water converts to 2 aluminum trihydroxide plus 3 dihydrogen. The electrolysis of water is a simple but expensive method of producing hydrogen. Typically, the cathode electrode is made from platinum. Subsection 2. Industrial syntheses. Hydrogen can be prepared in several different ways, but the economically most important processes involve removal of hydrogen from hydrocarbons. Commercial bulk hydrogen is usually produced by the steam reforming of natural gas. At high temperatures, 700 to 1100 degrees Celsius, 1300 to 2000 degrees Fahrenheit, steam, or water vapor, reacts with methane to yield carbon monoxide and dihydrogen. Specifically, methane plus water converts to carbon monoxide plus 3 dihydrogen. This reaction is favored at low pressures but is nonetheless conducted at high pressures, 20 atmospheres, 600 inches of mercury, since high pressure dihydrogen is the most marketable product. The product mixture is known as synthesis gas because it is often used directly for the production of methanol and related compounds. Hydrocarbons other than methane can be used to produce synthesis gas with varying product ratios. One of the many complications to this highly optimized technology is the formation of coke or carbon. Methane converts to carbon plus 2 dihydrogen. Consequentially, steam reforming typically employs an excess of water. Additional hydrogen from steam reforming can be recovered from the carbon monoxide through the water-gas shift reaction, especially with an iron oxide catalyst. This reaction is also a common industrial source of carbon dioxide. Carbon monoxide plus water converts to carbon dioxide plus dihydrogen. Other important methods for H2 production include partial oxidation of hydrocarbons. Methane plus half dioxygen converts to carbon monoxide plus 2-dihydrogen, and the Cole reaction, which can serve as a prelude to the shift reaction above. Carbon plus water converts to carbon monoxide plus dihydrogen. Note: hydrogen is sometimes produced and consumed in the same industrial process without being separated. In the Haber process for the production of ammonia, the world's fifth most produced industrial compound, hydrogen is generated in situ from natural gas. Subsection 3. Biological syntheses. Dihydrogen is a product of some types of anaerobic metabolism and is produced by several microorganisms, usually via reactions catalyzed by iron or nickel-containing enzymes called hydrogenases. These enzymes catalyze the reversible redox reaction between dihydrogen and its component 2 protons and 2 electrons. Evolution of hydrogen gas occurs in the transfer of reducing equivalents produced during pyruvate fermentation to water. Water splitting, in which water is decomposed into its component protons, electrons, and oxygen, occurs in the light reactions in all photosynthetic organisms. Some such organisms, including some algae and cyanobacteria, have evolved a second step in the dark reactions in which protons and electrons are reduced to form dihydrogen gas by specialized hydrogenases in the chloroplast. Efforts have been undertaken to genetically modify cyanobacterial hydrogenases to effectively synthesize dihydrogen gas even in the presence of oxygen. Other rarer, but mechanicalistically interesting routes to dihydrogen production also exist in nature. Nitrogenase produces approximately 1 equivalent of dihydrogen for each equivalent of dinitrogen reduced to ammonia. Some phosphates reduce phosphite to dihydrogen. Section 9. Applications. Large quantities of dihydrogen are needed in the petroleum and chemical industries. The largest applications of dihydrogen is for the processing, upgrading, of fossil fuels, and in the production of ammonia. The key consumers of dihydrogen in the petrochemical plant include hydroalkylation, hydrosulfurization, and hydrocracking. Dihydrogen has several other important uses. Dihydrogen is used as a hydrogenating agent, particularly in increasing the level of saturation of unsaturated fats and oils found in items such as margarine, and in the production of methanol. It is similarly the source of hydrogen and the manufacture of hydrochloric acid. Dihydrogen is also used as a reducing agent of metallic ores. Apart from its use as a reactant, dihydrogen has wide applications in physics and engineering. It is used as a shielding gas in welding methods such as atomic hydrogen welding. Dihydrogen is also used as a rotor coolant in electric generators at power stations, because it has the highest thermal conductivity of any gas. Liquid dihydrogen is used in cryogenic research, including superconductivity studies. Since dihydrogen is lighter than air, having a little more than 1/15 of the density of air, it was once widely used as a lifting agent in balloons and airships. However, this use was curtailed after the Hindenburg disaster convinced the public that the gas was too dangerous for this purpose. Hydrogen's rarer isotopes also each have specific applications. Deuterium, hydrogen-2, is used in nuclear fission applications as a moderator to slow neutrons and nuclear fusion reactions. Deuterium compounds have applications in chemistry and biology in studies of reaction isotope effects. Tritium, hydrogen-3, produced in nuclear reactors, is used in the production of hydrogen bombs as an isotopic label in the biosciences and as a radiation source in luminous paints. The triple point temperature of equilibrium hydrogen is a defined fixed point on the ITS 90 temperature scale. Subsection 1. Hydrogen is an energy carrier. Having been used as an ingredient in some rocket fuels for several decades, hydrogen, or more specifically dihydrogen, is now widely discussed in the context of energy. Hydrogen is not an energy source, since it is not an abundant natural resource and more energy is used to produce it than can be ultimately extracted from it. However, it could become useful as a carrier of energy, as elucidated in the United States Department of Energy's 2003 report. Among the various alternative energy strategies, building an energy infrastructure that uses hydrogen, the third most abundant element on Earth's surface, as a primary carrier that connects a host of energy sources to diverse end uses, may enable a secure and clean energy future for the nation. The hydrogen would then locally be converted into usable energy either via combustion or by electrochemical conversion into electricity in a fuel cell. One theoretical advantage of using dihydrogen as a carrier is the location and concentration of environmentally unwelcome aspects of hydrogen manufacture. For example, carbon dioxide sequestration could be conducted at the point of dihydrogen production.